Hey, hello. This is my lecture on bandit agents or multi-armed on the multi-armed bandit problem. Okay, I'm Till. So most of the stuff that I'm gonna cover in this lecture, you can also read up in this reinforcement learning book by Sutton and Bartow, if you like to read stuff. Also, um, you don't have to watch this video. Everything I say here, I will repeat in the lecture. So this is just for you if you want to have a sneak preview, or maybe if there's something in the lecture that you feel like, oh, you want to hear again, then watch the video. Okay, have fun. Okay, so what is a multi-armed bandit? This is a metaphor. It comes from the slot machine where you like pull a lever and then you get a certain amount of money, and this is kind of random how much money you get. Usually you lose. That's why it's also called a one-armed bandit. And then, some computer scientists said, let's call it a k-armed bandit or multi-armed bandit. And there the problem is you have lots of these arms, and you can pull them, and depending on which one you pull, you get a certain reward. Let's say you get a win of 1,000 euros or 10 euros or 0 euros, and there's some probability distribution, some randomness involved on how you get this. So that's probabilistic. Reward is what you get after you pull a lever once, and there's a probability distribution. So note here that the reward is really a technical term that we will encounter later as well. Okay, and then you pull these levers, or you pull these arms, and then depending on which arm you pull and depending on your luck, you get some rewards. But what we're interested in the multi-armed bandit problem is the value of each arm, or specifically we try to find the arm with the highest value. So the value would be the average reward. So here we don't know the average rewards. We can only guess them. And the way to guess them is we look at all the rewards we got so far for an arm and then divide it by the number of times that we looked at this. So here, for instance, for arm 1, we pulled it twice. We got the reward 5 and 2. So the approximate value would be 3.5. And we know by some laws of probabilities that this approximate value will converge towards the actual value. Okay, so and then the question is how to pull the levers in order to figure out which arm has the highest value. And the other problem is to over time also figure out gain this reward, right? So you're often in the scenario where you're interested in the reward, and you may have only a limited time horizon how many times you can pull these levers, right? So maybe you don't know, maybe you know exactly 30 times you can pull a lever. Maybe at some point it will stop, and you don't know when it will be, but until this point you want to maximize the reward that you got. Okay, so let's look at an example to see where this model could be applied. So let's say you have your news webpage, and there's a guest coming. You don't know anything. You're not using cookies about this guest, and you have these 3 newspaper articles. You have these news. I don't know, one article about Corona, one article about war in Afghanistan, and one article about that some prince in some country died. And then what happens is you can choose which article to present. And depending on which article to present, they might either click on it and read it, or they may ignore it and leave your webpage. And of course, you want them to stay as much as possible on it. So and there could be some hidden value. For instance, Corona, they click 50% of the time, war in Afghanistan 25% of the time, and then this prince, they click 60% of the time. So if you would know this, you would always present first the article about the dying prince. But at first you don't know this, right? And you gain through experience, you see which is clicked more often, which is clicked less often, and then in this way you can make a choice. And each guest appearing is another instance of way you can pull an arm. So here you're not in control on when you will pull an arm and how often. But you may know in advance that you expect, every day, usually 10,000 people visit my news page, so you kind of can estimate this. And so you want to figure out those numbers so that you can show the right article. Okay, so that would be an example where you can phrase a question as a multi-armed bandit problem. Okay, so as a first assignment that we would do in class, we don't do it in this video, obviously, but you can do it at home if you like. I would like you to think about examples in groups of size 2 or 3, and think about an example that involves games, because we're game and media technology here, and think about an example for farming. Just want you to think outside of a box, and creativity drives some constraints. Think about what are all the options. So for an example, you need to know, okay, how many options are there in the multi-armed bandit problems? The number of options should be fixed. So think about how this probability distribution may look like. Think about what would be the possible rewards that you get, and maybe think about what could be the true values of each option. So that would be question 1. Question 2 would be also try to think of non-examples. So that sounds silly because you say me pouring a cup of coffee and enjoying a coffee is a non-example because there are some properties missing, right? So maybe they aren't even an option. But think about maybe something that could look like an example, but then there isn't, and then think about why you think that isn't. There are also some scenarios which are a little bit controversial, where maybe it could be or it could be not. Think about properties that would make an example or a non-example. So this would be something we would do in class. Okay, now let's look at the application of the multi-armed bandit problem that we will have here. So we will have this game where you have to make a certain shape. Here it could be one of those 4 shapes, but these shapes could vary, the winning shapes. And let's play. So, let's say black starts, and then it doesn't really matter where white plays. The black can play here, and now white is lost, because next time black can play here, or black can play there or there, and in each case black would win the game and white cannot block all of those. So let's say white tries to block this one, and then black wins there and wins. So in this game, we will apply the multi-armed. This can be phrased as the multi-armed bandit problem to find the next move of this game. And so how to do this, let me explain in the next slide. Okay, so you have this empty board, and you just want to know what move to do. And in order to figure this out, you do a rollout. So that means you think about a random agent, could also be a different agent, but for now we work with a random agent, and that random agent you say, okay, you start here, and then you let the random agent play against itself until you win or you don't win. And then you look, this is called a rollout, so you just let the random agent play against itself till someone wins. And then you look on what are the winning probabilities. So for instance, if you win for these rollouts 50% of the cases, and this seems to be a better move than if you only win in 25% of the cases, and if you win in 66% of the cases, this seems to be, an even better move. And of course, this random self-play, this rollout, is not it doesn't give absolute truth, but it's if you would play against a random agent, then this would give you some help, right? And it would give some indication on what could be better or what could be worse. And here, okay, this is a multi-armed agent, so each action that you could take would be one of these options that you have. The reward would be you either win or you don't win, and the value would be the percentage of cases that you win if you would play infinitely, if you would do this infinitely often. But of course, we can't do these rollouts infinitely many times. Okay. Yes, as I said, this would be if you win with this option or not, this would be the reward, but actually the percentage, how often you would win, that would be the value. So distinguish here between value and reward. Okay, there's a subtle difference here that I have not mentioned before. So in the multi-armed bandit problem, usually the aim is to maximize the reward that you get over time. So that is, you may not get the best option, but you got the second best option. But that's still nice. But here somehow, or you just pick this very often, the second best option. But here in our scenario, we just want to know what is the best option, and we don't mind if we pick many times a bad option just to explore it, because we don't know what we gained in the time in between. We just care for, hey, what is actually the best move in the end. So we could just do only exploration moves if we like to, even if lots of them are stupid. In the end, it doesn't really matter so much whether you want to maximize, find the highest value, or you want to maximize the reward over time. It is more of a technical difference. In the end, this will lead more or less to the same behavior. But I just want to mention the subtle difference. Okay, so how to solve this multi-armed bandit problem? There are a bunch of strategies. Strategy 1 is eps-greedy. And eps-greedy kind of consists of 2 different types of strategy. So, okay, let's imagine we have some initial values already. Just pulled every lever once. And then there, let's say, strategy 0 before you come to strategy G1 would be just pick every option with equal probability. That's maybe not super sophisticated, is like not really a good thing to do, but I think that's the simplest thing that you can do, and this is called an exploration strategy. So just explore, you just think all options, can be equally good. Just pick any of those. And there is another strategy which is called exploitation strategy or greedy strategy, where you just always pick the best option you have so far. So that may not be good to figure out what is the best option, right? But if you think, maybe I don't have that many more times that I can pull a lever, don't have so many more tries, let me go for the stuff that is best so far. Okay, then that could be a good thing. That's called an exploitation strategy or greedy strategy. Then an epsilon greedy does, and here it's a little bit confusing, in epsilon of the cases, explore, and in 1 minus epsilon of the cases, take the greedy option. Take the best option so far. And that strategy is surprisingly working surprisingly well. And just as a little exercise for yourself, you can stop the video if you like. If epsilon equals 0.3, what is the probability that you would pick option D? Okay, if you want to think about it for yourself, stop the video now. Okay, now I give the answer, and it's 0.76. I hope you got the same. So in case that you take the greedy option, that would be in 70% of the cases, you would take option D anyway. And in case that you take an exploration, that would be with 30% of the cases. Then you would put this with 20% probability, so 0.2 times 0.3 is 0.06, which you have to add here as well, in case that you explore. Okay, that's epsilon greedy. Okay, so because epsilon greedy is so important, there will be another assignment in class. You can also do it at home by yourself. I want you to think what happens if epsilon equals 0. So yeah, you could, or what happens if epsilon equals 1? This is, neither of these cases are really great. Think about why that would be. So there's a need to have a balance. So can you maybe explain why you need to have the balance? Specifically, please write down in words why does exploration help the greedy strategy? But also, and that's maybe a little bit more counterintuitive, why does a greedy strategy help also exploration? So that's really a question I want you to think about and write down the answer and discuss it in your group. And another exercise to plot the returns over time. So you think you would get some reward. Of course, let's idealize it and let's think about an idealized situation that you could imagine, where for different epsilons, how would you imagine how much return you would get over time? Obviously, at the beginning, you would not know what the optimal option is, so you would get a little less of a reward. But later, you may have figured out one of the best options, so you would get a higher reward. So try to draw this graph for these different values of epsilon. Okay, feel free to do it at home or with a friend. Otherwise, I think it's best to do it in class. Okay, so there are some subtleties about the epsilon greedy strategy that I have not told you about yet. So let me use the opportunity to tell you about it. So one subtlety is, so when you think about it, specifically about the last assignment, you somehow have some start time when you don't know anything about things, and then you have an end time where you may already know a lot, right? You may already know, okay, these 3 options are really good and all these other options seem pretty shitty, and you want to think about when do you want to exploit more and when do you want to explore more. And the answer is, at the beginning, you want to somehow explore more, right? You don't know anything yet, and that's kind of also in real life. You're young, you want to go to festivals, you want to get to know more people, and then you're older, you get rid of it. You only want to hang out with your friends because you don't want to get to know new people. You made enough exploration moves in life, and so there is a variant of the epsilon greedy strategy, which is called epsilon decay, where you start with a higher epsilon and then decrease it over time. So that would be like a little variation or a little detail I want to tell you that what you could do with epsilon greedy. Another thing that I wanted to tell you is so how to set the start value. So I said maybe you pulled every lever already once, and that gives you some initial value. But you could also initialize a value. So you could just say, for every option you get a reward of 0, or you think you had already a reward of 0, although that's not really true because you don't know anything, right? Which is different to thinking it's 0. And that would be called pessimistic initial values. And there's also something that's called optimistic initial values. So optimistic initial values lead you to doing a little bit more exploration, even if you do a greedy strategy, because you took a greedy strategy, maybe you picked that option, and then that option now, let's say you got a reward of 4, then the approximate value would be 52. So it's like the worst option. So if you take another greedy, you would take any option with equal probability except that one. So it kind of leads to a little bit more exploration at the beginning. So that could be something nice. There is a somewhat odd phenomenon, which is, so you explore more, so you're not initially with the, so here the blue curve is the optimistic value, optimistic initial value. So you would kind of explore more. So at the beginning, you would take a little bit longer to figure out what a good value is. And then at the k plus first option, what happens is that you see a spike on the average, and you should think about why this is. So this is here kind of an idealized curve. So one of the homework questions will be, why is that? Okay, so that was epsilon greedy. Now take a break and come back so that you get the next strategy, which is upper confidence bound. Okay, so let's to motivate this upper confidence bound. It's kind of an odd name. I want you to think about the scenario we're having here, where we explored already many options, and I want you to think which option you would pick next, right? And I already can tell you that option D here, right, has the highest value or highest approximate value so far from what we saw. And A, C, and E seem to have a pretty low value. And option B has a value which is, or an approximate value of 6. So it seems pretty close to option D. And now if you think about epsilon greedy, what epsilon greedy would do if it would explore, it would take all the options with equal probability. But somehow that's not what we want. Like intuitively, we would want to take option B because that's a really good candidate for being the best option, right? We just haven't explored it so much yet. So you would want to explore that next because you're not really interested in bad options. You don't want to know how bad is option A. You want to somehow know, is maybe option B better than it appears? Is it maybe the best option? So you see here, we look at the approximate value that we have so far, and B is almost as good as D. But B has been tried much less often. We've just been a little bit unfortunate here. So somehow what you want is if something has a high approximate value, then we want to take it. That would correspond to the greedy. But also if we haven't explored it that often, that's also a criteria, right? And the upper confidence bound has this weird formula which tries to balance how good is the approximate value and how often have we explored this. So here, this symbol means the sum over all the rewards we received for this option, for option I. Here, how often we have tried option I. C is a parameter which tries to balance these two things, and you should think problem specifically how to set this parameter. And then this says the total number of tries, and this here tells us something about how often option I has been taken. So basically, this thing here becomes larger and larger the fewer times we have taken option I. But the whole term becomes also larger the more the more tries we had in total. So this kind of is a little bit of a weird formula, and I think it is related to how to compute the variance and how much variance you would expect depending on the number of tries that you had. So that would be the upper confidence bound. Pick the option for which this formula is maximized. And here that would be option B. Okay, I think these two strategies are the most important ones. You in your assignment have the choice to pick any strategy that you like, as long as it's a multi-armed bandit strategy. But you can also go crazy, right? So just in order to go a little bit crazy, I want to tell you one very simple strategy, which is, you rank all the options. You have a best option, second best option, third best option, and so on, and just pick the best option with a fixed probability, let's say always 30%, and the second best option always with 25, and so on and so forth. Just make sure that these options add up to a probability of 1. And you can have also different type of formula depending on other parameters, which tells you which option you try next. So yes, this is just to make you think about more different options to have. Okay, so there's something I don't want you to do for the first assignment, which is using domain knowledge. I kind of call it Pinocchio strategy because it can be a little bit, well, it would be cheating for this assignment. So these strategies based on these multi-armed bandit, they will not, perform overly amazing, but still they will have a good performance. But I want you to think about domain knowledge. Domain knowledge means that you know something about the situation, specifically that you know something about the game that you're playing. And so I want you to think about it yourself. So this is a little bit more difficult. So I remember that last year students struggled a little bit. So imagine, we have this game from the assignment, maybe with that winning shape or different types of winning shapes. How would an agent look like that uses domain-specific knowledge? It may not use some general AI strategy. You just know how the game works, and then you use that in order to try to win. Try to describe such an agent. So that try to really write it down in a group of 2 to 3. Think about what are the advantages of this agent, right? So think about how difficult may it be to implement it, how difficult may it be to prove it, how strong do you think that agent would be. Think about downsides, why you may not want to have such an agent. Yes, so that would be a task to be done in class. And of course, in class, I will tell you also my thought on this, but I cannot do in the video because obviously then I would give it away for the assignment. Okay, and then, so now you know what multi-armed bandit strategies are, and you know how to use them using these rollouts to get a good bandit agent for the game, and then you need to test it, right? And what you should think about these tests is maybe first is you really need to integrate tests early on. Try with the simplest possible agent, try the simplest possible test, and then do something more complicated, and then do something more complicated, and then do something more complicated. But don't rush forward and make this awesome agent, which all these ideas that you already had, just then to test it, and then it fails, and you do these very complicated tests, but you haven't done simple tests yet. So really try really simple and then advance slowly. By the way, I'm not sure what the last person here is meant to symbolize. Okay, so now what you can test is you should test different types of agents, and you can test them under different scenarios. So for instance, you should try different board sizes. You should try different winning patterns. You should think about, what if I can only do 10 rollouts? What if I can do 1,000,000 rollouts, right? So try to take both into account and test both. And then you have these hyperparameters for eps-greedy. For instance, this epsilon. For this upper confidence bound, there is this balancing parameter C, and you have to figure out what's the right parameter, so you have to test it under various parameters. That would be something to test. Then after you performed this test, right? So a test would be, what would be a test? It would be actually maybe playing this agent under the scenario and just physically play it. You know, you're the opponent, and see what you think about the behavior of your agent, and then just use common sense and think about how it could be improving, which situations it's missing, where you feel it could do better at that situations. At the beginning of the game, also at the end of the game. But then you also want to do some more organized testing, where you let your agent maybe play against a random agent for 100 times and see how well does it actually perform. So this gives you some more statistical data, and this will also be your evaluating criteria, where we of course check whether your agent is actually a multi-armed bandit agent. And then after we check this, it is necessary that your agent performs well. Let's say we play 100 games against a random agent, and if your agent, just plays as good as random, you're not going to pass this assignment. So you want to do that as well, because in that way you can learn also something, and that can help you to set these right parameters. Okay, and once you do the testing of this simple agent on the different scenarios that you observed, only then think about something more sophisticated that you can do. Only then try to improve. It's here what I'm telling you is not so much what to do, it's more of how to do it. Okay, but of course, this is something you learn by doing it, by failing on it, on making bad experiences, and then you will do better, and your programming experience will help you to think about in which order to do what and how to prioritize in order not to waste your time. And if you do it in the right way, this exercise, this assignment, you can do maybe in 2 days. But if you do things the wrong way around, you will run into a lot of dead ends. Okay, a last assignment I would like you to do. Think about the simplest possible test that you could do and that you could start with. But I also want to let you think. You have to do this programming by yourself, but I think you should really discuss with as many other students as possible what would be your favorite agent. Why would you pick that agent? What type of sophisticated tests you would do? Like, what test strategies you would have after you did a simple test. What would be maybe the next step? And then also think already about what could be some optimization ideas, and try to discuss it in the group, what ideas you think will be useful and which ideas will not be useful. You can also think about this at home, but I think it's really good that you think about this yourself. And in class, I can also tell you my thoughts about this. Of course, the final truth is how good your agent performs, not what I'm thinking. But so we did this last year, and students told us what they did last year, so I have a better idea of what can work and what did not work so well. But of course, I'm not giving it away, because this is your task to figure out. You can discuss with your fellow students, but ultimately, you should figure this out by yourself. That was it. I'm really looking forward to meet you in class next Thursday, and discuss with you many things. If you have questions, then this would also be in class the perfect time to ask those questions. Thank you.